All right, welcome to today's explainer. We're jumping right in because I am absolutely pumped for this one. Today, we're doing some digital forensics. We're tearing down the back end of a mobile app, layer by layer, to solve a classic architectural puzzle. Usually in development, you're forced to pick sides. Do you want the robust, mobile-first ecosystem of Android, or do you want the heavy-duty, data-crunching power of Python? But what if I told you, you don't have to choose? What if one could operate completely undercover inside the other? That's exactly the setup we're cracking open today.
To ground this whole thing, we're looking directly at the source code for a specific project. Check out this console output we pulled straight from the source file. It reads, "Welcome to Tactical Legends, Rise of the Austrian Salix." Sounds like a pretty epic, gamified setup, right? But behind this whole fantasy front, there is some incredibly smart, dry, and frankly brilliant syntax pulling the strings.
Just a few lines down in that initial Java output, we see the real ambition of this project. Prepare to command elite squads, forge relics, and shape the fate of Osteria. I mean, that is a massive promise to a player, and as developers, that immediately sets off alarm bells. How on earth do you build the computational engine for something that complex? You're talking heavy math for combat resolution, intense state management, maybe even some custom AI logic for those elite squads.
So to figure out how they pulled off this operation, we're going to trace the app's anatomy in 5 steps. 1. Enter Tactical Legends. 2. Bridging Android and Python. 3. Equipping Python dependencies. 4. The Python solver script. And 5. Executing Python from Android.
Okay, step 1. Enter Tactical Legends. Let's start by looking at the cover, the foundational Java environment where this app begins. What we have here is your completely standard run-of-the-mill Java entry point. It's the classic main class wrapper featuring a public static void main method. Inside, you see those system.out.println commands. Those are literally just printing out the grand welcome messages we were just looking at. It's highly structured, it's safe, but let's be honest. Standard Java can be a huge bottleneck when you're trying to quickly iterate on complex data logic or tap into specialized math libraries.
Which brings us to step 2. Bridging Android and Python. So here is the million-dollar question. How do you inject Python's insanely flexible, heavy-hitting data capabilities directly into a standard Java or Kotlin Android environment? You need a bridge, or more accurately, you need ChacoPy. Think of ChacoPy as a universal translator. It's a plugin specifically built to let you run Python scripts natively inside an Android application. So instead of spinning up remote servers or painstakingly rewriting your Python algorithms into Java, ChacoPy lets both languages live in the exact same house and talk to each other totally under the radar.
So how do we establish this connection? Let's look at the Gradle plugins block from our source file. Step 1. The script calls id com.android.application. That's just the app declaring its identity, telling the build system, hey, I'm a standard Android app. But then, right next to it, in step 2, it drops id com.chacopython version 15.0.1. It is explicitly installing this specific version of the ChacoPython environment right on top of that Android foundation.
Scroll down a little further in the build file, and it locks this whole operation in. You see it applying the plugin for the Android application and applying the plugin for the ChacoPy Python bridge. By doing this, the app essentially becomes bilingual. It's ready to compile your standard Android UI code while secretly hosting a fully native Python environment in the background.
Moving on to step 3, equipping Python dependencies.
All right, so we've got our hidden Python environment, but right now it's totally empty. We need to tell our newly built bridge which specific Python tools to bring in to actually make the logic work. Check out this beautifully simple block of code embedded in the project setup. It's a raw Python pip configuration block. If you write Python, you know pip. It's the standard package manager. Right inside the Android build file, we're declaring install numpy, install requests. We're pulling standard, heavy-duty Python ecosystem tools directly into a mobile project. It's so clean.
And honestly, this right here is exactly why developers go through the trouble of doing this. NumPy is the absolute gold standard for heavy math, matrix calculations, data manipulation, exactly what you need to crunch combat algorithms for something like Tactical Legends. In requests, it's famous for handling HTTP network requests elegantly, maybe for pinging a secure server for state updates or leaderboards. Having access to these specific libraries natively saves you hundreds of hours. You don't have to reinvent the wheel in Java.
All right, step 4, the Python solver script.
Our toolbox is loaded up. Now we need to find the actual Python logic hidden inside this Android app, the real brains of the operation. Notice where this file lives, app, source, main, Python, mysolver.py. It's pretty fascinating because it perfectly mimics standard Android directory conventions, but it carves out this completely dedicated, isolated space just for Python. This script, mysolver.py, lives right alongside the normal Android layouts and resource files, hiding in plain sight.
When we crack open mysolver.py, this is what we find. Now, obviously, there's a missing D in the function definition syntax here, desfiel a f add a comma b. But typos aside, what this script is doing is incredibly important for this proof of concept. It's defining a simple function named add that takes variables a and b and returns their sum. Right now, it's simple, but this represents your standalone Python logic. This is the placeholder for what could easily be a massive, complex data algorithm just waiting in the wings to be activated.
Which brings us to the final piece, step 5, executing Python from Android. This is where the whole operation comes together. We built the bridge, we imported the tools, we wrote the undercover script. Now we need to see the exact moment the Android codebase reaches across that bridge and triggers the Python file. Picture this on two sides. On one side, you've got your compiled Kotlin or Java code running the UI in the app lifecycle. On the other side, you've got this embedded Python environment holding the game logic. Let's watch them talk.
First thing that happens on the Android side, val.py equals python.instance, boom. With that single line of Kotlin, Android reaches out and summons the Python environment into existence. It wakes up the interpreter we configured, so it's fully prepped and ready to take orders.
Then, look at the precision here. The Kotlin code calls val module equals py.getModule mysolver. It specifically targets the exact mysolver.py file we were just looking at in the directory tree. The bridge is no longer just connected to Python generically, it has locked onto our specific hidden logic file.
And here is the actual execution. The Android side triggers module.callAttribute add 3.4. It explicitly calls that add attribute, our Python function, and passes the numbers 3 and 4 right through the language barrier. And since Android requires strict data typing, it immediately tacks on .toInt at the end, converting whatever dynamically typed response Python spits back into a perfectly strict Kotlin integer.
The result of all this architectural heavy lifting, the Python script takes the 3 and 4, crunches the math natively, hands it back across the Chaka-Pi bridge, and yields a perfect 7 back on the Android side. It's a massive, complex cross-language bridge, pulling off a flawless handoff in milliseconds.
So here is the big takeaway. We just watched it add 3 and 4. But imagine swapping out that basic addition for a massive NumPy matrix calculation, a localized machine learning model, or real-time encrypted data parsing. The limits are totally gone. With Python operating completely undercover inside Android, what kind of complex logic are you going to build into your next project? Seriously, I hope this breakdown gave you some ideas. Thanks for joining me on this deep dive into the source code, and I will catch you on the next explainer.